Okay, so welcome to this final video in the hashing and hash function unit, I guess. In this video, I'll just sort of wrap up with some of the conceptual last little pieces and I'd look at sort of an extension of the idea of a hash table to kind of a larger issue, or not issue, but a larger goal, I guess. Yeah, I think that's about it for this video, which probably will be a little bit shorter than some of the others, since this is mostly just final thoughts and things like that. So just very, very quickly, so a hash table, of course, right, is this idea of organizing our data by assigning it to a location. So in the strategy that we looked at for doing so, and that are coding, is called chaining, which says, well, if you have data nodes that are supposed to be in a certain location, of course there's by default kind of space for one, but if you have more than one, then the chaining strategy says that you should just say, oh, all right, well, if you need more space, if you have more than one thing to go in a certain location, then use a linked list rather than just a traditional array, and instead use an array that has pointers, an array of, you might say, an array of first pointers. And where do they point to? Well, each pointer points to a growing and or shrinking list of nodes that you can then say, oh, all right, well, if I need to insert something else into a certain row, I can just prepend that node to the row, and that way I'm still doing the hash table. So the idea is that even though I'm not going to necessarily find things immediately, I'm still going to find things more quickly than if they were just in a traditional array or just a regular linked list, because I have the ability to say, go to the right place where this thing is going to be stored. And either it's immediately there, like if I'm looking for the number 24, then when I go to slot 3, it's the first node. So look how fast that is to find. Now let's say I'm looking for 31. Okay, I mean, it's not the first thing I see, but when I go to the next node in the linked list, 31 is there. So all right, not too bad. That's two nodes. This is better. This is much faster than anything we've looked at. Linear searching, binary searching, it's faster. There's a million offshoots, of course, of hash tables and other things you might do. I mean, these little the lists that we're looking at, that one and that one. If I look at this slide, you could then have those sorted numerically, like in ascending order, so that you could then do binary searching on that row. I didn't have you do that because I didn't want to completely kill you. But you could, right? Or you could do anything, right? Any sort of other additional criteria that you want to put, you could do. If you don't want to do prepend, you could do append at the end, or you could do in-order insertion. You guys wrote code for that when we did a double linked list. So you could make these double linked lists, right? So that they sort of go both ways. And then you could do an in-order insertion so that the list is always sorted, right? Then you don't even have to bother to sort it. Okay, anyway, so all the stuff that we could do with linked lists, we could do with each row of our hash table. All right, so that's not what so you're working on coding a hash table. We talked about it here quite a bit. We wrote a program, well, sort of together, or I wrote one in class and talked you through it at least. So you have that code as a starting point. So hopefully you're having good success this week and over the weekend that you had a chance to work on the program number 3. I think it's labeled in Canvas, which is the hash table program. It sort of incorporates everything we've really done for the last, month or so, I guess, at this point. In terms of recursion, it's in there. A class is in there because you're making it into a class. And then, of course, the stuff we've done with hashing more recently. Anyway, so hopefully coding and getting that off the ground. I think the only main function that we didn't really talk about is deleting, which you do have to do in the program. But we've done deleting, right, or removing. I mean, we've done that in a lot of contexts. In fact, probably almost everything we've done in the semester, removing has been a part of it. So it's not super foreign in in a hash table. So kind of borrow some ideas probably from some of your linked list programs to get a handle on how to do that. But again, within a hash table, you're still just doing a series or a collection of linked lists. So for the most part, that code that worked on a linked list should work on a hash table. You just have to go to the right linked list, right, within the hash table. But anyway, okay, so hopefully coding is going reasonably well. So a couple of last things, though, to think about or to talk about in terms of designing your hash function and your hash table and all of that. So we talked a little bit about the beginning in our intro about how hashing is used, and of course it is used, as we've been reinforcing, as a means of having a smarter and more clever way to store and then later on locate data, so that we have assigned locations for things rather than just essentially what order did you come to me in is the order that I stored you. So that's good, right? But we also talked a little bit about a hash function, about hashing being a way of doing a little bit of at least light encryption. And encryption, meaning translating your data into something that maybe at least is not super apparent what the data actually is. So for sure, I mean, this is obviously far beyond anything we're doing, but you all have an appreciation for the idea that large data sets are, of course, stored on a variety of servers for any sort of application or any sort of industry that you can think of has databases as a significant portion, I guess, of their business. So what does a database designer do when they're trying to decide, well, how should this be stored? So we will look at a light idea, at least, of thinking about, well, the hash function. That's the thing that's sort of telling us how we're going to store it, or what's the organizational structure. So choosing a hash function, now we're not going to sweat this too much, but this is actually a very difficult task to do, and for sure, even if you're using some sort of a mod function, that's fine, but well, what number do I mod by? Well, we're going to talk at least a little bit about one of the easy things to consider when choosing the right mod function or hash function in general, but if we're modding, how do I decide on n, right? So if we're using, this is what you're using in the program and that we used in all of our examples, is that you're taking whatever the key value is and you're modding by n. And of course, the thing that's nice about that is that when you mod by n, of course, you get the remainder when you divide by n, which of course is going to be some numbers 0 through n minus 1, which lines up perfectly with an array, because of course an array has slots numbered 0 through size minus 1, right? Or n, if we're saying n is the size, n minus 1, right? So, but we want to but there's a little bit of a balance here, right? We want to make sure that we have enough space for our data to go into our hash table, but we don't want to do so excessively. So the next few slides sort of talk about the balance between these two. So before we get to the punchline, let's at least first consider, if you're doing a bad job of this, what does that mean? So let's consider a hash function, which is modding by 10, which is probably an example that we looked at, right? Or at least I think we did. I think we looked at mod by 10 or whatever you're doing in your program. So we're using in real life what would be terrible hash functions. Now we don't care too much because we don't care about security and we don't necessarily care about some of these constraints, but real people do. So what would be terrible if I used modding by 10 as a hash function? Well, two reasons why that's probably awful. The first reason, so if you're modding by 10, then of course I'll just draw a little hash table here. Then of course your slots are just 0 through 9. Right? So those are So those are our table pointers. Okay, so if I only have 10 options, which of course if I mod by 10, I only have 10 options. Let's say you have 1 million data elements to stick into this hash table. Well, if I've got 1,000,000 nodes to insert into this hash table, and I only have 10 rows, that's kind of how I think about these, right? I have 10 rows. Well, then on average, each of them is going to have about 100,000 entries or nodes, which means these linked lists, right, that are sticking over here, sticking out of each box, out of each slot of the array here, these are going to be really, really long, right? In fact, on average, you'd have about 100,000 sticking out of each of these. I don't want to draw all these in, but you know what I mean. So these would be probably pretty enormous. Well, so how much am I really saving by knowing something? Oh, okay, let me come back up here and say I'm searching for the number, 381. Well, 381, okay, that would be in row 1, because I'm modding by 10. But if there's 100,000 boxes here, and I'm looking for 1, I'm still going to have to look through on average half of them. So that's 50,000 boxes I'd have to look through. I mean, that's better than 500,000, which is how it would be if it was in an array or a linked list. But I'm not really saving all that much time because the lists sticking out of each row grow to be a little bit probably too long to really be worth it. So that's one concern. The other concern about modding by 10 is that, of course, if the value, right, the key value that I'm using, let's say it's some sort of ID number or account number or something like that, well, if you mod by 10, you're automatically, when you mod by 10, you just get the ones digit of the number. So if this is sensitive information, a password or whatever, some sort of sensitive thing, when you mod by 10, you reveal the ones digit. Now, maybe the whole number, maybe it's a social security number, so there's 9 digits. Is there 9 digits? Yeah, 9. So, okay, knowing one of them is maybe not a crisis. But, of course, data needs to be protected at all costs, or whenever you can. At least you need to sort of be as safe as you can. So you don't really want to ever reveal any of the digits. So modding by 10, not only does it create this kind of enormous logjam, but it probably also isn't the most secure thing in the world, because now, of course, the person would have to know, or the hacker would have to know that you've modded by 10 in order to know that you're getting the ones digit, right? But you could sort of conceivably see patterns and whatnots with this that would make you sort of say, oh, well, gee, all the numbers I seem to be getting are between 0 and 9. Oh, okay, well, that probably means you modded by 10, because otherwise how would that be, right? So in real life, and we're not going to talk about this because this turns into much more of a math class or math conversation than anything else. In real life, what is used as the modding number instead of 10 are usually large prime numbers, is what are usually used. Prime numbers because you don't have any other divisors, which makes it helps with encryption and security, and large numbers so that you have a variety of possible remainders, so that it's not just 0 through 9, making it harder for people to figure out, well, what are they modding by? So in real life, there's an insane amount of art and math and security that people who do that do in order to come up with this right number. So the second point here, the this is not terribly safe, is a much harder question. But to unpack this first comment, let me frame this discussion here of these two competing interests. So I think in general in computer science, when we think about what seem to sort of be at odds with each other, is often speed, which we know what that means, is usually at odds with, as a consumer, usually at odds with price. So in other words, speed and price are related in the sense that if you want something fast, of course you have to pay more. So there's a relationship between these two. Now in that sense, right, with cost, they sort of go the same way. But these two, right, so speed, which I define here, at least in what context I mean speed, is in competition instead of in harmony, I guess, with memory conservation, or how much memory you need in hash tables. So let's look at this. So what do we mean when we say speed? So by speed, since the main purpose of a hash table is to store data, how would I rate speed, or what does it mean to say, oh, this is a fast hash table? It means that you would be able to find things very quickly. And how does that happen? Well, in a hash table, I'll flash back to the little mini picture I drew. Up here, this is a slow hash table because the lists are very long. So, of course, the opposite is true. So what does it mean to say that you have speedy hash table, or speed in hash tables comes from making the lists that you have to look through short, or as short as possible. Because, of course, if the lists are short, then you can quickly find what you're looking for. Well, that makes sense. And how do we get short lists? We get short lists if we can reduce the number of collisions. So the lists only become longer when you hit collisions, when you have two, or when you have a subsequent thing that's trying to insert itself into a row that already has something. That's what causes these lists to become long. So if you could reduce the number of collisions, this would mean your list would never be all that long. And since when we search through the hash table, we're going to scroll through these lists, you would be able to find things very quickly. So this is sort of like oh yeah, well, why don't we just always do that? Okay, well, here comes the rub in the second part. So how do I make that happen? Well, in order to have fewer collisions, you'd need to have more slots. So your array has to become very long, right? Or you have to have a lot of space in your array. You need a very tall array if we're drawing this up and down. Because, right, that's the only way to avoid collisions, is to say, well, you know what? I'm going to make space, lots and lots of space, so that at most only a few nodes collide when they're trying to fill in these slots of the array, or these rows of the hash table. Okay, that's fine, but what's going to happen if I say, all right, if I mod by a big number, right? Modding is going to be our way of hashing. So if I say, all right, I want to have 100 million slots. So I might mod by 100 million, so that I have lots of slots. Okay, but what if I have a million things to put into that? Oh, well, a million nodes to insert into 100 million slots means that lots of them are going to be empty. Right? I mean, think about it. Some of them might collide, and you might get some lists. So if you have, again, 100 million slots and a million data nodes, that means, of course, that means only 1% of the, not necessarily 1% of the slots, right? But that means you have 1% the amount of data as you do slots. So of course, in an ideal world, those all sort themselves out nicely, and you're only using 1% of the slots, each of which has one node sticking out of it, and the rest of them have nothing. Okay, probably that doesn't actually happen just because of the way that the data probably comes in. There's probably some collisions, but yeah, you'd end up with a very tall, a very tall array, but very short lists sticking out of each slot. So that's great for speed, but in order to make that happen, you probably have an awful lot of empty slots, which means you've allocated memory for this array to be enormous, but didn't really actually use most of it. Well, of course, this is where we say, well, now, of course, you've been bad at memory conservation, and you've wasted an awful lot of memory, and memory is money. We know that, I'm sure, that memory, when you're building a machine or using a database or anything like that, the capacity of it is, of course, directly linked to the price. So you say, I need 100 million slots. What if each one of them costs, a penny? Well, you got to spend $1 million to build that. Somebody else might say, hey, I could do that with 100 slots. That costs $1. Oh, well, I know who I might hire for that job. The person is only going to charge me $1. Okay, right, so these things are in competition with each other, which makes sense, right? Fast, if you want something fast, it's going to be more expensive, or if we put it in this context, if you want something fast, it's going to be bad at conserving memory. It's going to be very wasteful of memory, because that's the price you pay for it to be fast. So you might say, all right, well, I'm going to go with the other guy. I'm going to go with the one that only cost $1. Great. Okay, so now we're back to sort of this situation, where I think I said 100 a second ago, right? But okay, 10 slots or 100 slots, even if you have 100 slots, and you're putting 1,000,000 data elements into each. Well, now that means you've got tens of thousands of nodes sticking out each row. So how do you get good memory conservation, aka cheap? How do you make this a cheap project? Is that you reduce the number of slots in general, but of course that means, of course, you also maybe are reducing the number of ones you don't use, because of course that means you can store this in less space, and space is money, so it's cheaper. So we'll make the array smaller, which saves memory and money. However, what's going to happen? Well, if you have fewer slots, then when you put your data in, you're going to end up with far more collisions, which means the lists will end up being much longer. And of course that's bad, because this means that later on when I go to try to find something, it's going to take a lot longer. All right? So, again, this makes sense with our notion of human existence, right? Speed is always good, I think, and I don't think there's ever a situation where you don't want things to be as fast as possible. But of course, that means that memory conservation is going to be poor, aka cost is going to be high. All right. So of course, what are you really doing, or people who work in databases, what do they do? Is of course you decide which is more important, speed or money, right? Memory conservation. So if you need something fast, and you sort of say to yourself, well, I'm Amazon or I'm Google, and so I have lots of money to spend on databases, but I need it to be fast because my customers won't put up with slow times. Then you might say, all right, well, I'll err on the side of speed being the thing I care about the most, and memory conservation be damned, right? I'll go with whatever's the fastest. On the other hand, right, if you say, well, it's mostly an internal product, right? Maybe it's not something that customers are using. It's just you and maybe it's a startup and a small staff. You say, okay, it might take 30 seconds for you to do a query because you have very long linked lists. But you say, well, that's okay, right? We're a small business. We can do that, but it saves an awful lot of money. So maybe we go that way. In reality, I think you end up striking a balance, really, is probably what happens most of the time, is you shoot somewhere in the middle. And you say, well, I'll spend some money on this, but not crazy amount, because I want it to be at least kind of fast, right? That's, I think, what ends up being the case. And of course, if this is in the business setting, maybe you start out with something that's slow but cheap. And then, of course, maybe if you have more customers and more data to store, and you're doing a little bit better, you do an upgrade, right? That's kind of what that's all about, right? Why do people get service upgrades, which is mostly just increased memory and service on that, right? Is to make this adjustment. So, so the last thing I want to talk about is something that I used to make the students code, and when I get to the slides that have the pictures, you'll be thankful that I don't actually that I'm not actually having you code this anymore. But I did want to at least discuss this with you, and may ask you a little bit about this later on. But so one of the original goals, so hashing, which has hopefully been a good topic and an interesting topic, the idea of using a hash table, had a couple of goals, right? One was this ability to get to data quickly, which we've discussed that to death. This encryption piece of being able to assign locations to data, but maybe do so in a somewhat secretive way, or at least not obvious way. But a third thing that I think we listed or mentioned at the beginning of our notes on this was the ability to do this. So the ability to store data, but to be able to do so with maybe more than one, right, or we might say dual criteria. So the idea here would be that we would have a hash table, because we hopefully are appreciating that that's a good thing. But a hash table is only going to be organized by how you hash whatever the key value is. Again, so let's go back to our classic example of student data. So ID number, fine. So I use the ID number as my key value for hashing. So okay, great. But now what happens when I want to look something up by name? In fact, in your program, I think you're doing a search by two different criteria. Now, of course, the one you have a good way to do it, and the other you have not such a great way to do it. But what if you wanted a great way to do both? So is there another way for us? Is there a way for us to somehow double hash or dual hash or some, as it might be called, but without having to sort of do it? Now, one solution, of course, to this, I didn't type this into the notes, but one solution is, well, you make a hash table by name, and you make another hash table by, let's say, ID number. And then if the user says, I want to search by name, you go to the name the name hash table. If they want to sort by ID, you go to the ID hash table, right? So I guess that is one way to do it, but that requires no additional knowledge, I guess. But of course, you can hopefully appreciate that, once again, that's very wasteful. If I'm going to actually make two entire databases of the same data, but one is organized one way and the other is organized by some other value, that probably doesn't seem super efficient. So is there a way to sort of have it both ways? And I'm presenting to you here an idea of how you can do that, which isn't that bad. So what's the idea? So maybe I have some other, like I said, I maybe want to do one thing with hashing, but then my second feature is maybe some alphabetical sorting if I have names or whatever. Maybe there's some other numerical value that I want to be able to sort by, maybe address or something like that, or maybe just write some second key value. So how might we do this? So I'll show you a picture of this on the next slide, but if you want to try to do this, you want to try to store dually sorted data, then one way we could do this is to say, all right, for your data nodes, you can still make a regular hash table as we've been talking about all week. Great, fine. So do that, you put them in, you have a key value, you use that, and you do your linked list. Okay, great. But also, I put this in red because you're going to see in the diagram that this is going to be in red. You can also weave another linked list, probably a double linked list, just because it'll help you with deleting and whatnot, through the same nodes. So the same is caps for a reason. So I'm not going to just redo it and say, let me have a names hash table and an ID number hash table. I'm going to still say, fine, I have an ID number hash table, period. But then those nodes, what we can do is we can weave a linked list or double linked list through those nodes and at least have them listable or listed or connected via some other search criteria. So maybe name. So if I use ID number to put you in the hash table, great. But then I could also weave this double linked list through the nodes by name, alphabetical. Now I'm not going to be able to hash by name, but I would still at least know that I have a way of then getting to the nodes in alphabetical order, which means at the very least I could do some more efficient searching if I know that they're in some sort of order. All right, so let me show you an example. It's way easier to see in an example than me just describing this. So this kind of is a lot to look at. So let me start by pointing out that in blue down here is the hash table. Now I know we've been drawing it vertically, but the book put it horizontally, so we'll go with horizontal. But so in blue here, and then in black, so ignore all the red for now. In blue and in black is just our regular hash table, and they're modding by 11. So the nodes you can see here, hopefully, right? So just again ignore all the red. But in black and in blue here, out of slot 0, when you're modding by 11. Oh, okay, 99 mod 11, right, that goes in evenly, so the remainder is 0. So 99 is here, 22 is here, 33 is here, okay, and so on. There's some other numbers over here, which are hopefully in the correct slots. Okay, so that's the black, so that's what we've been talking about all week, so that's nothing new. But what is new is that what's also here, sorry, let me not use red, so that, I'll go green here. What else is, though, in here is all of this red stuff. So follow the arrows with me if you would here. So they use some books use the term header. This is essentially first. Okay, so if you don't like header, go ahead and call that first if you want. And instead of trailer, you can call that last if you'd like. But what is the red all about? Is that if you look at the numbers, so now look at the numbers in the circles here. 22, which has the header pointing to it, or we would have called it first pointing to 22. I think that's the first number in numerical order. And then what's after that? If I follow the arrow, 31 is after that. And what's after that numerically? 33. And then 36. And so on 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 and so on. And 99 is the largest value numerically. So this, what you see in red here is just, it's a linked list that you could insert, or you could weave is a good word to say. You could weave that through your hash table. Now again, this doesn't let me find things by number. In this example, right? If I'm using the same value to do the hashing and the linked list organization, that's probably a little overkill. Usually you would probably use some other value, again, like a name or something like that. But for the sake of space here, they figured they'd just use the same value here. But what's beneficial about the red is that if I wanted to list these in numerical order, all the nodes, right, which is the thing, right, you might want to display all of your data, obviously in some sort of order would be even better. I would still be able to print this list of, I think there's 10 numbers. I could print these 10 numbers in order from smallest to largest by simply starting at first, printing, and saying go to the next one, 31. Go to the next one, 33. Go to the next one, 36, and so on. So you would have the added benefit of being able to run through the nodes via either the same or an alternate organizational criteria. And you can't do that with just a hash table. Right, so if I just have the black and blue in this picture, I don't really know how I would, in any sort of clever way, print my data in order from smallest to largest. I mean, there's no way to really do that, because 22, the smallest number, I mean, I have no way of knowing that that's the smallest number, unless I've, would search through all of them, I guess, or something weird like that. I guess I could do it, but... So there's benefit, right? There's definitely benefit to doing a secondary organizational structure. And in a lot of cases there are, right? In a lot of cases when you think about a database which lets you search by more than one feature, which most would, or most do, it's something like this, right? It's more sophisticated, obviously, than what we're looking at on our screen here. But this is the general idea of how you would build up a more complex network, I guess, of organizational structures onto your data. So in case this example isn't clear, I think I have a little animation here. So let's say the list, the table is as is. So again, remember the black and blue, that's the hash function. That's the hash table. But then the red is just straight up numerical order, low to high. So if I was going to insert the number 52, well, the first thing I might do is say, well, I have to hash it because it's going to go in a hash table. So I hash it, and if I do 52 mod 11, I guess you get 8. So it would say, oh, okay, the new number should go in slot 8. But there's a collision because there's already a 63 there. So of course I would do the usual thing, which is move, is it moving? Yes. Move 63 up and insert 52, a prepend, right? Do the usual prepend thing. All right. So of course I would say, okay, great. So I prepended 52. It's now before 63, which used to be the first node. Now 63 is the second node. Great. These both have a remainder of 8. So for the hash table is sort of happy right now. But if I'm going to try to also maintain this red business, this low to high linked list woven through this, I might have a sort of phase 2 of inserting. Now the node is here, 63. It's really here. And I, inserted and all of that, and I probably have some sort of a temp at least pointing to that, so that you know how it is when you insert, you're doing some action. I'm sorry, what was the number? It was 52. I'm sorry, 52. Right. But 52, while it's been inserted in the hash table, has not been inserted in the red. So I'd have to sort of throw back to an earlier program or some earlier ideas where we said, oh, when you do in-order insertion, you have to start at the beginning of the list and scroll until you find nodes for which the value that you're going to insert belongs between them. You guys wrote a program to do this, right? The in-order insertion, where you sort of scrolled through and you looked and you said, okay, I have to stop once I get to the point where the number is supposed to belong. And then, of course, we do so 47 and 53, that's where 52 should be inserted in the red. Whereas right now, of course, 47, what's coming after 47 right now is 53. But since I just inserted 52, I would, of course, want to do a little bit of rerouting and have that go here. And then from 52, it happens to be right next door, I could then connect that to 53, which I think is what you see on the next slide. Oop, one more. There. Okay, so if you were going to code this again, I stopped giving this as the assignment because it just got to be a little bit too hairy. But if you were going to do this and you were coding insert, you would do the insertion, the prepend, which you've already coded, or you're coding. Or we coded last week together in class. But then you'd also have sort of the extra task of saying, well, let me also make sure that the linked list, the red, is squared away. And same thing for removing. If you were going to remove, for example, 31, you might first, let me hash it first. So if you hash 31, you get a remainder of 9. So I'd go to slot 9, and I would search. I'd start at the beginning, and I would say, is this the one I want? No. And then I'd go to the next one and say, is this the one I want? I'd say, yes, 31 is. So if I'm going to remove 31, similar to inserting, you have sort of two phases of removing. Perhaps the first thing, I might have done too much there. Let me go back for a sec. Okay, so I'm on this picture. So how am I going to remove 31 if 31 is going to go away? Well, one thing I'm going to have to do is take note that on the red pointers, 22 pointed to 31, and 31 pointed to 33. So if 31 is going to go away, I for sure need to reroute this one to point up directly to 33 so that I can eventually snip 31 out of the list. So that's one thing I would do, is reroute the red pointers to get 31 ready for deletion. And then, of course, I also have to think about the fact that 31 is part of a hash table, and in particular it's part of this black linked list right here. Now this happens to be the last node, so there isn't a whole lot of rerouting or anything. But of course, if I was deleting 53, for example, I'd have to do something like make sure that I adjusted that pointer so that when 53 would go away, 31 would move up to be the first node. But in this case, since I'm removing 31, there isn't much to actually show, but I certainly would adjust any other of the black pointers, the table pointers, to legally remove the node. And then notice, this list is still good. This hash table, I should say, is still good. I didn't mess up the black. Everything is still hashed in the right spot. And the red is now also okay. 22, that's beginning. 22 points to 33, and 33 points to 36. Okay, so I removed 31 successfully. All right, so of course, in order to do that, and this is more of a comment on where we're heading next week, is that in order to do things that are a little more complicated, which that certainly is, right? Each of these nodes, let me circle any one of them, I don't know, 50, 52 maybe. If you think about a node now, okay, so a node has maybe, if I'm doing a double linked list especially, it's got a prev, it's got a next, and it's got a next in the table. So I would count 3. In fact, let me clean up my drawing here. I think every node in this table here, if you count how many pointers come out of it, if it's remembering that the red is a double linked list, each box or each node would have 3 pointers. So you'd actually have to sort of upgrade a little bit here. We've mostly been doing just a next pointer for our hash tables, or we had done earlier a double linked list, which has next and prev. Well, if you want all of that, that's fine. But now, of course, we're going to upgrade to say that you would now need 3 pointers sticking out of each box. Maybe I would even say 4. If you make the hash table a double linked list, you might also have a hash prev if you want that to be a double linked list. But for sure, right, you'd at least want to have these 3 pointing out of each box, which means how bad was our life when we switched from linked list to double linked list? Mostly it just added 1 extra line everywhere because you had to update prev in addition to next. Well, similarly for this, right, if you were going to actually code this, which you're not, how much worse would this be than the hash program that you're currently working on? Is that you would just have to say, well, you're already doing that. So you just need to throw in another extra couple of lines in order to keep track of a few more pointers. Now, where we're headed after this week is, and where we'll spend the rest of the course, is in what are called trees and graphs and heaps and a couple of other kinds of names, where we're going to actually end up having 5 pointers sticking out of each box eventually. And the benefit there, I mean, obviously that probably sounds like it's going to be a lot of work, and maybe, well, I guess it sort of will be. But the benefit of increasing the number of pointers sticking out of each box is you have that many more links and connections to to other nodes. Obviously, that's what the pointers do. But sort of organizationally and structurally, by increasing the number of pointers, you're coming up with a richer and more efficient design for yourself. You're letting yourself have more options for how you're going to organize the data, which is, while coding-wise, going to lead to, instead of 1 or 2 lines for each, maybe it's going to be 3 or 4 lines or 5 lines of update this pointer, update that pointer, and stuff like that. Yes, that's true. But in terms of efficiency, we're going to see a big improvement, continue to see even more improvements as we add to our headache, right? I mean, more is worse in terms of coding, but it will be faster and we will be more efficient. And once we get to trees, especially, you're going to see that there's a huge savings there. I think that's the end. That's it? Yeah. Okay, so this is a little bit of a shorter video, so that's just not a problem at all. So just a reminder, and I'll fill a little bit of time here at the end by giving you an outline for the week or ideas for the week. So this is the end of notes. So program 3, which is the hashing class, is due Wednesday. So like I said, hopefully you've had a chance over the weekend to get into it. If not, start sooner than later. It's a program instead of a lab, so it's probably going to take you a little bit longer. But it's I know I probably say this, but it is mostly patching together those stuff that you've already done. There isn't a whole lot that's like brand new in terms of ideas. I mean, hashing, but I don't think that's too crazy. But for sure, look at the program that we did last week. It's posted under notes. So I think if you go under, I don't know, I have Canvas open, but I like to do it. If you go under notes, I think you'll see from last week's video, you'll see not only the videos that you watched last week and the notes, the slides and whatnots that we went through, but here it is right here. But the sample program is also here. So you could so this is the one that is from the video, so you're welcome to look at that. The assignment has, what's the reading assignment? The assignment itself has some starter code, which is mostly the code that we wrote. I think I dressed it up a little bit and modified it ever so slightly, but so check that out for sure for some ideas. And a lot of the tasks that you're doing, you're just doing stuff on a linked list. So recycle some of your old programs and recycle, like for example, you're going to do deleting on a linked list, a single linked list. Well, I should say you have the option. You can either make it a double linked list if you want, or leave it single. But we did both. You did both of those already in a previous program. So while you can't just cut and paste, what I would do, I mean, you can cut and paste and then massage though, because you got to sort of make it click in the lingo of what you're doing. So you can't just cut and paste, but you can certainly steal the idea, or at least sort of the pseudocode of how you would go about doing it and adapt it for this. The other thing that you're doing in this program is you're doing a class, which you've already done one. You did the Q class, which I think went pretty well for most of you. So that's, again, a little different, that it's a class, but it's easier, I think, to do stuff in a class. So, okay, anyway, so good luck with this, and hopefully the program goes all right. And then on Friday, we'll do a quiz. So I clicked ahead. This is in Canvas, right? But you can click on, there's something, quiz number 2, recursion, double linked list, stacks, queues, classes, and hashing. So we'll do that on Friday. I think I maybe had Wednesday down at some point as a thought, but I want to give you time to work on your program this week and not have you worrying about doing that and also studying. But quiz number 2 is going to be on Friday of this week. So what is that? Friday the 17th. Okay. So we're going to do this during our class time. I know we haven't done anything sort of live or synchronously, as the term is being thrown around now. But we will do the quiz, so to speak, live. I'll send around some details about this this week, but we will do it Friday around 11. I won't necessarily say exactly at 11. And it'll be paper and pencil. So I will have you either print out. I'll give you. You'll have access to a PDF, which is the quiz. And I'll have you, if you want to, you can print it out if you have a printer where you're at. If you don't have a printer, it's fine. You could just you could just pull it up on your phone or on a screen so that you have it, and then you can complete the quiz just on blank paper is fine. But you'll do it, you'll complete it, pencil and paper as you have done in the past, and then I'll have you scan and upload your pages basically to this Canvas assignment here. And that way I can look at them, like I normally do on paper, and grade them and do the usual stuff. So, so I'll send you details about that. But just as you're planning, I mostly wanted to say there are practice problems here. In fact, I guess there's a couple of sets, or there's one here, and solutions, and then extra practice with solutions to those. I guess I wrote a little bit of code here for one of the questions on there. So check that out this week. A quiz, I should just say, we did one other quiz, which was a quiz for us is basically an exam. It's just that it's a 1-day exam instead of a 2-day, like the midterm we had a few weeks ago. I mean, that was an exam, sort of capital E exam. But these quizzes, the one we did in, I guess, February probably, and then now this one, are sort of like the in-betweens. Like they're the exams that are in between the big exams, so to speak. So I say this to you to say this is our second of 2 quizzes. So this is it. So we did the one again in February, and then we have this one, and that's all. So that this will close out that category of grade in Canvas. So so you do want to obviously do a good job on this, and I would treat this like an exam. So take time this week, in addition to completing program number 3. Take some time to study, to get yourself organized. Obviously, it's an open notes exam, because I wouldn't be able to stop you from using your notes, even if I wanted to, which I don't. I mean, I think it's totally fine to have that. But do study. I think that a big mistake that sometimes people make is like, oh, cool, I can use my notes, so like I don't need to study. And it's still going to be a timed exam, so it's not like you're going to have, 10 hours to ponder and scroll through notes and watch videos and do all this other stuff. You're still going to have to sort of move quickly. So, but anyway, I probably said a lot of the details here in this video, but I will send this to you in an email as well. So that you can have all of that in place. On Wednesday, so this is the Monday lecture video that you just watched. Wednesday would have been a review day, or I would have given you these review problems and printed them out. So we'll stick with that, right? So we'll say your class lecture thing on Wednesday is do these practice problems, right? Print them out if you want, or just do them on paper. And obviously check your answers and see how you did in preparation for the quiz on Friday. So good luck with everything. As usual, if you have any questions, please feel free to reach out via email and or Zoom. Send me an email if you do want to Zoom, and I'll send you the password, I guess that's what they call it, to get into the Zoom room. So if you have questions on anything, feel free to reach out this week. And like I said, I'll be in touch, I don't know, Tuesday or Wednesday probably with details about Friday's quiz.